Okay, before we begin graphing, let's talk about what happens when our exponent is greater than 3. So we have f of x equals a to the n, x to the n, plus blah, 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 right, all the way down to your constant. When n is greater than 3, the graph is going to resemble one of two functions. It's going to resemble either y equals x squared or y equals x cubed, depending on whether n is odd or even. Actually, you know what we're going to write? We're going to write even or odd, just because I wrote x squared first. Even or odd. So when n is even, the graph is going to resemble y equals x squared. And when n is odd, the graph is going to resemble y equals x cubed. And I really should have used a different color here. I don't want to use yellow and green on that same. Okay, there we go. So remember that y equals x squared it's a little off center. Still a little off center, but we get the drift. And when here's y equals x cubed. So there's y equals x cubed. So notice how our n's are kind of working together. They're doing the same thing on x squared. However, on x cubed, they're not. And you might remember this from another algebra class where we talked about the n's doing the same thing, n's doing different things. Both rise, both fall, one rises, one falls. So we'll be talking about those two. So let's get to this graph. We have y equals x plus 2 all raised to the 5th power. So this is an odd degree. So it's going to resemble y equals x cubed. So if we look at y equals x to the 5th, y equals x to the 5th is the parent function. We're going to be able to put a 0 in, and we get a 0 out. When we put a 1 in, we get a 1 out. When we put a -1 in, we get a -1 out. And when we put a 2 in, we get 32 out. Holy smokes. And when we put a -2 in, we get a -32 out. So this is really let me show you what's happening here. If you use your graphing calculator and zoom in, you'll see that this graph is doing something like that. Now it's going to kind of appear flat right there towards the origin. But we know that this parent function is being translated 2 units to the left. 2 units to the left. So this tells us to take our parent function and move it 2 units left. So we translate those points and we get a graph that looks like this. Now it says specify the x and the y intercepts. The x-intercept is the value of x when y is 0. So I put a 0 in for y, x plus 2 to the 5th power. I'm going to 5th root both sides. I can also think of it as raising both sides to the 1/5 power. 0 to the 1/5 power is still 0. And 5 to the 1/5, the 5th power to the 1/5 power gives me just x plus 2. So x equals -2. That's one way to do this. Another way to do this, and really it's completely up to you, is taking the 5th root, and you still get 0 equals x plus 2, x equals -2. So our x-intercept is -2, 0. That's our x-intercept. Our y-intercept, the y-intercept is the value of y when x is 0. So we have y equals 0 plus 2 raised to the 5th power. Well, 0 plus 2 is just 2, and 2 to the 5th power is 32. So 0, 32 is our y-intercept. 0, 32. We knew that. That was going to be way up there. Here's our x and y intercepts. -2, 0. 0, 32 is off the chart, and that's how we graph y equals x plus 2 raised to the 5th power. That is a polynomial function. That is a polynomial function. Okay, here's another example. This time we have an even degree, and we have a bit of a vertical stretch. So we've got a vertical stretch and a reflect. That's going to be a reflect over the x-axis. And we're going to translate this right 3 units. So we've got lots going on here. So my parent function is y equals x to the 4th. Well, I'm going to plot that. When I put a 0 in, I get a 0 out. When I put a 1 in, I get a 1 out. When I put a 2 in, I get 16 out. So that's a bit up there. When I put -1 in, I get +1 out. And when I put -2 in, I get a +16 out. So we've got this graph right here. And again, when you put this into your calculator, if you put it into your calculator, you'll see that x to the 4th looks like x squared, but it's a little flat right here. So it's more of a U instead of a curved V. Now this graph, this parent function, has lots going on. It's got a vertical stretch of 2. Okay, so it's got that. It's got to reflect over the x-axis, so it's not going to be opening up, it's going to be opening down. And then it's moving right 3 units. So we always reflect first. So I'm going to reflect this, right? And I'm also going to impose that vertical stretch of 2. So instead of putting a 1 in and getting a 1 out, I'm going to put a 1 in and I'm going to get a -2 out. And instead of putting a 2 in and getting a 16 out, I'm going to put a -2 in and get -32 out. So this thing is going to be super skinny. We thought it was skinny before, and it is even skinnier. Even skinnier. Now this entire graph right here, after the, actually I better make sure I get all of this. This is all going right 3 units. 1, 2, 3 units. And that's our graph. That is our graph. So this is y equals -2 times x minus 3 to the 4th power. And you can see those ends are really dropping dramatically. They are, the further away from the vertex that I get, boom, those things are just falling, falling, falling. Now what are the x and y intercepts? The x-intercept, remember, is the value of x when y is 0. So negative 2 times x minus 3 to the 4th power equals 0. Divide both sides by negative 2 and I still get 0 equals x minus 3 to the 4th power. If I take the 4th root of both sides, I get 0 equals x minus 3, and x is equal to 3. So our x-intercept is 3, 0, and that indeed does match what our graph looks like. And our y-intercept, according to our graph, we can't even see our y-intercept. It's huge. That number is very large. So our y-intercept is the value of y when x is 0. So I'm going to have 0 minus 3 is negative 3. Let me show you all my work there. 0 minus 3. Negative 3 to the 4th power is a positive 81. Negative 2 times positive 81 is negative 162. That's going to be 0 comma negative 162. There's no way that we were going to be graphing the x and y. The x-intercept, yes, but not the y-intercept. So we weren't going to be able to graph that y-intercept because our graph just only goes to negative 10. Everything else falls far below that, right? Okay. We're going to get into more common graphs that don't rely on transformations. We'll be needing to do some test points, look at what's happening in between our x-intercepts. This is more typical of the type of polynomial functions that we deal with in college algebra, pre-calculus,